So hello dear students, welcome back. Today we have another problem from JAM 2025 and this is a little tricky one. It is the 14th question of the 2025's paper, and here we have V as a subspace of R10. There is a 10-dimensional Euclidean space. Suppose A is 10 cross 10 matrix with real entries, and for any integer k you define this set a power k bracket v, which is nothing but basically the image set of the matrix a power k when you multiply vectors from the subspace V. So this also means we have the trivial notation that a v is equal to a power 1 of v. So then the question asks about which of the statements is not true. So that is very important. Again, we have to see the incorrect statement among these four. And if you see, most of the questions are asking about dimension of either V or the set AV. So what are the concepts that are needed? Well, we will see the toolbox. So basically here you have a sort of linear map, right? This a power kx is mapping x vector to a power kx. Now that also means we need basic ideas of linear transformation and things related to them. So for any linear map A and subspace V, there is a formula which talks about the dimension of the set AV, that is the image set of AX where X belongs to V. So this set has dimension equal to dimension of V minus the intersection of V and kernel space of A. So this is again very important, and what it gives us is that this dimension of AV is greater than equal to, because dimension of V intersection kernel of A is less than equal to dimension of kernel space of A. So if you take a minus, it will be greater than equal to, and this will be a lower bound sort of, where the dimension of kernel space is nothing but the nullity of A, basically the dimension of the null space. So that is there. And also a very important observation is that if A is invertible, which is indeed in one of the questions, that is A non-singular, then A restricted to V, that actually means a very simple thing, that is like you are having A restricted to V is a map from V to R10 where you write this as A U for U belonging to V. So that means this is invertible also implies that the dimension of this image space, it will remain unchanged, it will not alter, as we know that multiplying with a non-singular matrix doesn't change the rank of a matrix. So the same idea goes here. So with the utilization of these results, we can now easily solve the question. So option A, it is saying that if A is non-singular, then dimension of AV is equal to dimension of V, which is indeed true, because A is non-singular implies kernel space is the null space. It has only 0 in the null space. So dimension of V intersection kernel space of A is the dimension of the set 0. So there is only one element, it has dimension 0. So this is indeed true. So option A is correct. What about option B? Option B says it is possible that A is singular and still dimension of V is equal to dimension of AB. Well, now this might seem as wrong, but this is not wrong, because we are not necessarily having this A into V. Here this A might not be full rank, but this may be true. well, if it was like rank of A is equal to rank of AB, that happens if rank of B is n, it is a full rank matrix. Multiplying with a matrix that is not full rank will not necessarily retain the rank of that multiplied matrix, that is rank of AB. So what is the logic there? Even if A is singular, it can be injective on a chosen subspace V. So by injective it means that it maps all elements to places except 0, right? So that means there might be the only intersection might be the set 0. So that means dimension of AV is equal to dimension of V. This is possible, and this is possible if this condition is this dimension is equal to 0, then it is possible. So that means option B also should be true. You might think a little bit on this, but this is like for special situations that A is singular, what you will do, you will see what is the kernel space or the null space of A. So that is all x such that Ax equal to 0. Now think about the entire set V, and from there you are perhaps taking out this set kernel of A. This whatever is left behind there, from there you can perhaps take the elements of V, and that will result in this intersection 2 is 0. So basically you will take a orthogonal space that is orthogonal to the kernel space, and then this thing will hold. Now next, upon the option C, we have that if rank of A is 8, then you have to say whether this inequality holds necessarily. Now this is a good question, because rank of A is 8 means nullity of A is 2, because it is 10 minus 8, that is 2 by rank nullity theorem, and that is 2 means the dimension of kernel space is 2, and if you are now computing dimension of V intersection kernel space, that is now less than equal to 2. So this is greater than equal to dimension of V minus 2. So basically you are just again utilizing this result, and more specifically you are utilizing this result that dimension of A V is greater than equal to dimension of V minus dimension of kernel space of A or nullity of A, which is same as this. So this is again true. Now it is actually enough to conclude that the last option is correct, but still for the sake of completion we will show that this option is not necessarily true. And what does it say? It says that dimension of V equal to dimension of AV equal to dot dot up to A5V, then necessarily A6V should be equal to dimension of V. So that means you are taking higher powers of A, and all the image spaces, they have same dimension up till 5, A power 5. Then you are sort of concluding that A power 6, for A power 6 also you should have same kind of dimension. The dimension should be retained, but that is not true in general, and that is shown by this counterexample. This might seem a little tricky, but it would be very helpful in a conceptual manner. So take A to be the nilpotent shift matrix. Basically by that we mean it is a matrix which is nilpotent, and you know nilpotent matrix is A power k equal to 0 for some k. It is 0. Some k strictly greater than 1. Basically if it is for 1, then it's the null matrix. Well, here many nilpotent matrices have this kind of a structure where the lower triangular portion including the diagonal is 0 or the opposite thing, and the elements are in the upward diagonal except the diagonal term, terms on the upper triangular portion except the diagonal term, and this kind of matrix often are nilpotent. by the sense that if you take a power 6, you can show a power 6 is 0. So, but here there are many things that are going on. To be more specific, you can have a into e1 equal to 0. That means the first column is 0. A into ej is ej minus 1. So that means the second column is e1, that is the first canonical basis. Third column is e2 because 1 is in the second position. So this a ej is ej minus 1 for j equal to 2, 3, 4, 5, 6, and after that it's all 0. So basically this is like just one portion of the matrix is Jordan form, and rest of the elements are all 0. So you might try to visualize this. This is little lengthy because it's a 10 cross 10 matrix. But the key thing that is happening is if you take V as a span of E6, then the image keeps shifting left. So that's very interesting. By the sense, if you take A times E6, that is E5, right? So what is A squared times E6? That is A E5, which is E4. So if 6 will shift to E5, that will shift to E4, E3, E2, E1. And if you multiply E1 with A, that will give you 0 because you already have that. So that means these dimensions will be retained up till a power 5. However, at a power 6, it will become 0. And that's why not necessarily this dimension should be same as all of this. Hence, D is not correct. So that was all for this question. With that note, I thank all of you for watching the video. Hare Krishna.